Today, we're going to take a journey right into the digital heart of architecture. We're going to trace how we went from drawing simple lines on a screen to building these incredibly intelligent, virtual buildings that you can walk through before a single piece of dirt is even moved. I mean, seriously, think about that question for a second. It sounds like something straight out of science fiction, right? But this is the big question that's driving all the technology in architecture today. It's all about creating, testing, and perfecting our most complicated structures in the digital world first. It saves just a ridiculous amount of time, money, and materials. So how did we even get to this point? Well, it really wasn't that long ago that architecture meant giant physical blueprints rolled out on drafting tables. And if you needed to change, say, a window on one drawing, you had to manually hunt down every other drawing and update it by hand. It was slow, and man, was it prone to errors. Now, we use these dynamic, data-rich models where you make one change and it ripples automatically across the entire project. The difference is just night and day. To really get this revolution, you have to understand the huge difference between the two technologies that define it, CAD and BIM. And this isn't just a simple upgrade, it's a completely different way of thinking. It's the difference between just drawing a building versus virtually building it. This right here is the key analogy. The best way to think of CAD is as a super high-tech electronic drafting board. It's amazing for drawing lines, arcs, circles, all that stuff. But BIM? BIM is a whole different animal. It's like a virtual construction site and a super detailed database all rolled into one. You're not just drawing lines anymore, you're placing intelligent objects. Let's break this down a bit. In CAD, a wall is just two parallel lines. It has no idea it's a wall. It's just geometry. In BIM, a wall is a wall object. It knows its height, what material it's made of, its fire rating, and how it connects to the floor above and the ceiling below. And this brings us to the most important point, coordination. In CAD, if you change the floor plan, you have to go and manually redraw the elevation view. It's tedious, and it's a huge opportunity for some really costly mistakes. And this shows the power of what we call parametric modeling. Because that digital wall is an intelligent object. Changing its position in the floor plan means it automatically updates its position everywhere else, in the elevations, the sections, you name it. This one feature alone saves countless hours and prevents so many coordination nightmares down the road. It is, without a doubt, a total game changer. But that object intelligence? That's really just the beginning. The true power of BIM goes way beyond just a pretty 3D model. We're talking about adding layers and layers of information to create what are called the dimensions of BIM. Let's take a look at how this turns a simple shape into a complete digital twin of a building's entire life. So, 3D, that's the geometry, the shape, we all get that. But then you add 4D, which is time. You link the model to a construction schedule, and you can literally watch the building get built virtually, spotting problems before they ever happen on site. 5D adds cost. Every single object gets a price tag, so you can track the budget in real time. 6D is all about sustainability, letting you analyze energy use to design a greener building from the very start. And, believe it or not, 7D is facility management. This embeds all the data the owner needs for the building's entire life, helping them run it efficiently for decades to come. Okay, so how do these incredibly complex models actually exist on a computer? To get how they're drawn, stored, and shared without being these gigantic, unmanageable files, we've got to quickly look at the two basic ways digital graphics are made: pixels versus mathematical paths. So on one side, you have vector graphics. This is what programs like AutoCAD use. They don't store images as a bunch of dots. They store them as mathematical instructions, like draw a line from point A to point B with this curve. On the other side, you have raster graphics, like a photo you'd edit in Photoshop. That's just a simple, fixed grid of colored squares, what we call pixels. And this is the critical difference for architecture, because a vector image is just a math formula. You can scale it up to the size of a billboard, and it will stay perfectly sharp. The computer just recalculates the math. This is absolutely essential for drawings that have to look good on a screen, but also be printed out on huge sheets of paper. A raster image, though, has a fixed number of pixels. So when you try to enlarge it too much, we've all seen this, the computer has to guess how to fill in the new space, and you get that blurry, pixelated mess. Its quality is completely tied to its original size. That's why just taking a photo of a blueprint is a really poor substitute for the actual design file. And you run into these file types all the time. The vector files, the ones that are so important for drawings, are things like DWG, DXF, and SVG. The raster files, used for photos and textures, are the ones you know well: JPEGs, PNGs, and TIFFs. Just knowing the difference is huge for managing design info. Okay, so we've got these really complex vector-based models. But here's the problem. The architect, the engineer, and the contractor are all using different software. So how on earth do they collaborate on the same project? Well, this brings us to our final and really crucial concept, interoperability. Interoperability is a big word, but it's a simple idea. It's just the magic that lets a project flow smoothly between all the different teams and all their different software. It's all about creating common file formats that act like universal translators, making sure that all that rich data from a BIM model doesn't get lost when it moves from one program to another. And these file formats are those key translators. The .dwg file is AutoCAD's own special format. To share that CAD data with other programs, they created the .dxf, the drawing exchange format. Now for BIM, the absolute gold standard is .ifc, or Industry Foundation Classes. It's this critical open source format for sharing all that rich model data. And last but not least, .stl is the format that lets us take a digital model and send it to a 3D printer to make a physical object. All right, to wrap things up and see what stuck with you, let's circle back to one of those key layers of information we can pack into these virtual buildings. What does 6D BIM stand for? That's right, 6D stands for sustainability. This is where the model gets used to analyze everything from energy performance to solar exposure, basically the building's overall environmental impact. This lets designers make huge, important decisions long before anyone even breaks ground. And this really brings us to the final point. This whole digital revolution, it isn't just about making things more efficient or having cleaner drawings. It's about giving designers and builders the power of foresight. This technology allows us to test, to analyze, and to perfect our world in a computer first, so we can build a smarter, more responsive, and a much more sustainable one out here in the real world. Thanks for tuning in.